Okay. Let's start. Class number 14 on October the 3rd. After the midterm examination, okay, the first one. So we're gonna talk about your midterm a little bit, and then you see how we solve all these problems and maybe know your mistake or know that you did things right already. Okay, so we're gonna spend some time on that, and then we can proceed to nonlinear geometry buckling problems and nonlinear solution strategies, which is gonna be the rest of the content for this course for this semester, right? So let's start. Problem number 1. I will use Microsoft Excel to solve things for you. I go to my favorite font, Canberra. Okay, 66. Okay, right. First problem. We will establish the stiffness matrix of the whole piece that is non-prismatic bar connected to the rigid element in the middle. Rigid means undeformed, right? And then another piece of this non-prismatic bar elements, and we need to establish the stiffness matrix of the whole piece of this thing, okay, having just 1 and 2 degree of freedom. So let's do it together. I will look at this as one element, this is as another element, and this link, your degree of freedom will be tied up, because if this moves to 1 unit, this is going to move 1 unit as well. So okay, problem 1. I know that the stiffness matrix, okay, then I cannot crop the picture right now. Okay, I just use print screen maybe. No, doesn't work. Okay, fine. So this one is element number 1, this one is element number 2. First of all, we're gonna have all degree of freedom like 1, 2, 3, 4 degree of freedom like this, and then we will finalize, consolidate everything, come down to just 2 degree of freedom. So 1, 2 for element number 1. I call it U1, U2, and it's just gonna go quickly, right? Element number 1 and F. Oh, sorry. This is supposed to be U1, supposed to be U2, F1, F2. Basically, you're gonna have the whole thing in here. Okay. Being E and A over L, where the A is the average of these two. Well, we used to do this, right? So we know that E times A, which is 2A. Okay, the average of 3 and 1A turns out to be 2A. So multiply by 2EA over, what is the L? 2L, right? 2L. So 1 minus 1 minus 1 and 1. That's it. Element number 2, we have the same U3 and U4, F3, F4. Okay, exactly the same. And then your degree of freedom, as we know that U3 and U4 are, U2 and U3 are going to move together. So we put them together in one system of equation like this, 0 0, and as you share this, okay, so the stiffness matrix turns out to be F1, F2, or actually F3, and then F4, U1, U2, U4. Right. So right now, what you want to do is to find out the relationships. If you apply 1 unit displacement here, what will be the corresponding forces at the left node and the right node, right? That's how we come up with stiffness matrix. And the way we come up with stiffness matrix, you can, well, you can prove, integrate, come up with strain, do all those things, or you can use numerical technique like this, because over here I just use the stiffness of these two bars connected together, and then I set up a system of equation, and then I will apply things as I want. So okay, here is my stiffness matrix. Well, what should I do? I think I go with Lagrange multiplier, then I know the corresponding forces, right? So well, I have two. First of all, this is the boundary condition. Here is also the boundary condition. If I keep this boundary condition fixed, and this one I have the prescribed displacement being, let's say, 1. So let's see this together. I'll copy this down. Well, this is like a scratch node anyway. I just take the number down here. Okay. And then I will have 2 additional rows and columns. 0 them out and 0 them out. All right. So first of all, I will have the -1 here and -1 here, -1, -1. Right? That means I'm gonna enforce the boundary condition at U1 and U4. Okay, so this is U1, U4, U1, U4. Okay, so here is your right hand side. Basically, you have 2EA over 2L, then turns out to be ELL, which is equal to I should do this. Let me move it around. Okay. So this includes, I'll zero it out first. 0, 0, 0 -1 unit. Okay. So is 0 here because we moved the reactions to here, U1, U2, U4, and reaction, okay, R1 and R4. Okay. All right. Now that's it. Inverse the matrix and we try to get the displacement solution. MMUT of M inverse of this matrix multiplied by this known. Okay, so displacement 1 here is 0.5, here the right end equals to 0. You need the force equals to 0.5. Let's check the unit a little later. Okay, and minus 0.5, minus 0.5 is come back, right? 0.5 is coming in this way. So the unit is what? EA over L, right? Oh, just EA, huh? Or EA or L. Minus 1 is actually, let's check unit a little bit. Minus 1, okay, whatever. In order to get the unit here, this is multiplied by EA over L, L over EA, just move it to that side. Yeah, just EA over L. So if you apply 1 unit displacement, then you're gonna have 0.5 and minus 0.5 coming backward. Well, you do the same thing. So you just copy the same thing down to here, and then I'll just change to 0 and minus 1, and then I get this. Okay, I don't care about the thing up here, displacement solution. I just need the resulting reactions. So from this, I can establish the stiffness matrix, which is 0.5 minus 0.5 minus 0.5 and 0.5. Okay, that's it. Done for the first problem. 20 points. Second problem. Well, pretty much the same. You have a bar element again, and this bar element at the nodes, it is connected with the spring. Okay, so this spring resists the displacement in the longitudinal directions. So basically this is pretty much like a pile. Okay, so you have the pile driven into the soil, and then you have some sort of like soil spring resistance along the length, along the axis of the pile, and that is the visualization or idealization of the problem. So let's do it together. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 degrees of freedoms, and we have in total 8 elements. 8 elements, 9 degrees of freedom. Where is it? Which one? Okay. Element number 1. Well, all 9 degrees. Then you need to write down, show me. This is U1, U2, U3, okay? Because I will not know how you set things up. So without this, well, this is going to be the problem. So without the U1, U2, U3 written down, I don't understand your work. That's the thing. So here I'm going to say that here is my U1, here is my U2, here is my U3, and so on all the way to U9. All right? Do not run to me at the end of the class if you forgot these U1, U2, U3. I told you before the exam already that you need to explain your work. And F1, F2. So that's it. EA, constant cross section, L is 0.1 L, right? So multiply by 10 EA over L. That's it. And well, over here you know that you're gonna have like 9 degrees of freedom. So I will set up the things to just accommodate the whole system of equation. I set up this big matrix, and there you go, multiply. I drop the 0 first, right, element number 1, element number 2, element number 3. What? Sorry, I just want to do this. 3, 4, 5, 6, 7, 8, 7, 6. By the way, I think we have to start our class earlier, so 7:30 is gonna be the start time of the class. Okay, there you go. And then what? Minus 1. Oh, 1 minus 1 minus 1 1. Copy, this one is gonna be here, right? And then this one is gonna be this, and F4 U4, F5 U5, F6 U6, F7 U7, F8 U8. Okay, that's it. And system, the whole system, we're gonna have this add up with this, add up with this, add up with this, add up with this, add up, oops, no, add up with this, add up with this, add up with this. Okay, let me check. Okay, everything looks right. Then there you go. Copy and copy. There it is. Okay. We get the system stiffness matrix already. Then boundary conditions. And for the boundary condition, we have two boundary conditions. We have not incorporated the spring yet. We will soon. Alright, minus 1. And U9, minus 1. Minus 1. Minus 1. Okay. There it is. Oh, wrong one. Minus 1 here. Okay. Alright, and this is scaled by 10 EA over L. So what do we have? We have EA over L here at DOF2. I will add just EA over L. So this is plus 0.1, right? Because the outside is scaled by 10 EA over L. Okay. How about the F3? FU2, this is UT. So 2, 3, 4, 5, 6, 7. Okay, great. Easy to do. Plus 0.2, plus 0.3, plus 0.4, plus 0.5, plus 0.6, right, and plus 0.7. Okay, done. And that's multiplied by this whole thing. And then reaction 1 and reaction 9. Huh? Actually, it's nothing special or nothing's new here. So you have seen all this in the class. and you don't have the apply point force, just only have -1 over here. That's it. And solve. So you are going to end up with M inverse of this, comma this, close the bracket, and there it is. So you can see the distribution of the displacement start from 1 unit apply at the leftmost and then gradually decreasing along the way all the way to 0. You get 0 at U9. Well, that makes sense at least, okay? You post the condition that U9 has to be 0, you get 0. You post the condition U1 has to be 1, then you get 1, okay? And then you get 2 reactions, all right? So first you need the 0.329 AOL at the DOF1, and the resisting force is minus 0.01. The remaining force is taken care by the spring. So you don't see these two balance because it was taken by spring. Now I just copy this whole thing again and paste here. I guess it doesn't change. Okay. Oh well, I think I got to keep the value and numbering formatting, values and source formatting. Okay. All right. Change to 0 and -1. In order to get this, I need to just reformulate this. MMULT of M inverse of this matrix, close it, and this. Okay, there you go, and you get this. So you can make the stiffness matrix of the overall member U1, U9, F1, F9, multiplied by EA over L. Okay, so when you apply 1 unit at U1, you need 0.329. And when you apply 1 unit at U9, you have minus 0.01. Right? Likewise, when you apply 1 unit at U1, you have minus 0.01. And 0.55. Done. Second problem. 40 points.
How about the 10 times 10 ED over L?
This is scale. Yeah. So I can just put the 10 inside. All right. Thanks. The 10 is not there yet, so M inverse of that. Could it be 10 multiply? Is that okay with the argument there, like that? Multiply by 10, just like that. So 10 multiplied by the matrix before that we want to inverse. Okay. All right. Oh, so number change. Okay. And this. Thanks. So M inverse 10 multiplied by this. Oops. Okay. All right. So 0.328. Okay. Drop it here. Just the number and formatting, and 0.9009 something. Just to drop the number here. Okay, I'll up. Okay, this one here is coming. Well, actually just switch around, but yeah, actually it's the same number. And this one here, there you go. Okay, right, thank you for attending. Okay, done. Next, problem number 3. It's just a lot of geometry works, but actually if we how to say, we can group them, basically. So if we set up a good strategy to work on this problem nicely, then life will be not that bad. Basically, I think you jump to this one right away, because that's gonna be okay. You practice a lot on this thing, right? So you are pretty sure that you're gonna get the point from here, which is good. Okay, and then you can come back to this thing later. This okay, top and bottom chord, same cross-sectional area, so same stiffness, EA, okay, EA routing. Then 1, 2, 3, 4, 8, 16 members here. The stiffness matrix looks just alike, right? So you conduct the transformation once and that's it. How about this? 1, 2, 3, 4, okay. 4 members here will be alike, 1, 2, 3, 4, and these 4 are alike, and then vertical 1, 2, 3, 4, 5, 6, 7, 8, 9 are identical. So we have 1 kind, 2 kind, 3 kind, and 4 kind. 4 stiffness matrix that we need to compute. And 1, yeah, okay. 5. This and this are different, yeah. Okay, 1, 2, 3, 4, 5, yeah. 5 stiffness matrices you need to come up with. So I instruct you that the degree of freedom should be determined from the node number multiplied by 2, -1 for the x DOF, without -1 for the y DOF. For example, the node number 7, then the x DOF is going to be 14 minus 1, 13, and the y DOF is going to be 14, right? If you work in the 3-dimensional space, then we're going to take the node number multiplied by 3 minus 2, multiplied by 3 minus 1, and multiplied by 3 without minus. So the node numbering and the degree of freedom numbering are in the same system. All right. Then let's start. So the geometry of this truss, horizontal distance is 12 L, and the vertical distance from this point to this point here is equals to 5 L. So your geometry is falling into that triangle you learn in Pythagoras theory, 5, 12, and 13. Okay, and okay, the angle of the load is okay pi over 6. You can determine all these angles a little later. So maybe start with these chords, top and bottom chords on the on the left side, top and what is the 3EA? So your stiffness matrix, okay, you local first node, and let's say you start and you ending, okay, and then F start, F ending, okay. You start, you ending, three EA over L, so that is 3 minus 3 minus 3 and 3 times EA over L. That's it. And for this, you have to be consistent, as I mentioned before. If we want to measure the angle like this, if we have the x-axis going here and we want to measure from x-axis up like this, then this has to be the starting node and this has to be the ending node. Okay, so just need to be consistent if we intend to measure the axis like this, right? That's going to make the direction cosine. So you have the 2/4, right? Which one first? Cosine first, right? Cosine of the angle first, and then sine and cosine and sine. What is the cosine of this angle? Cosine of this angle is 12. Cosine. Sine is 5/13, right? For this angle. Cosine is 12/13. It's 12/13. 5/13. And then we get this stiffness matrix, which is going to be the 4/4, and that is equals to MMULT of transpose of this multiplied by MMULT of this and this. Hey, this is switching around. It's gotta take the 4, right? 4/2. So 4/2 is gonna, okay. Do I have? Okay. That is multiplied by EA over L. So this is the global U starting node X, global U starting node Y, U ending node X, and U ending node Y. F is X, just need F is Y, F E X and F E Y. Okay. Now, just got to drop things in. What do we have here in total? 18 degree of freedom. That makes 36. 18 nodes. That makes 36 degree of freedom. 36, right? 1, 2, 3, basically make it U1, U2, okay, U3, all the way to 36. Okay, then I can shrink it down a bit. Likewise, force 1, force 2, all the way to 36. Yes, and AT column. Okay. Yes, okay. Drop the 0 in. And then I can just take care of these fellows 8 elements first. I don't want to have like too many matrices of 36 by 36, so I'm gonna have 136 for the top and bottom chords on the left first. So start with the first one. Starting node is 1, ending node is 3. Okay. Starting node is 1, ending node is 3. So I'll do it this way. Maybe it just make life a little. Does it make life easier? I'm not so sure. Yeah, I think so. Few more. Okay. Should it be white or should it be? Yeah, I think it should be just white. Okay, just that. So this is copied. Okay, one by one. So first of all, this is going to be U1, U2, and U5, U6, right? Just to show you F1, F2, F5, F6. That's because 1, 2, and here is 5, 6. So copy 1, 2.
Sir, what about the length of the bar? Length of
I have not incorporated that yet. Sorry. Yeah. The length which is not well. This is what 13 divided by 4L. Okay. Thank you. Well. well, yeah. One second. It is this one, right? So I just fix it in here. Divide by, well, let's say multiply by 4/13. Huh? Okay. All right, that's it. Okay. So copy this in value without formatting. U5, U6 is here. Same as here. Okay. First element done. How about the next element? I look at this one. This one involves U5, U6, and then U9, U10, right? 5, 6, 9, 10. So come back here again. 5, 6, 9, 10. So it's gonna be in here, around here. So for here, multiply by 2. So let's say this is equals to this, right? Multiply by 2. Okay, and here is equals to this. Here is equals to this, right? And here is equals to this, right? 2 elements done. Next element 1, 2, 3. Next one 9, 10, 13, 14. 9, 10, 13, 14. So 9, 10, 13, 14. It's just like this. So basically this is actually equals to this. And here is equals to, yeah, this one. Here is this one. And here is this one. Okay, done. Next, this element. So 7 to 10, 10 is 19, 20. 19, huh? Seriously? Yes. 7, 8, or 9 is up there, 10 is out here. So 7 and 10, 10 is 19, 20. 7, okay, it is here. Then this one here, just put on top. Basically, you get the same as this piece. All right, 1920. 1920 is coming here. 1920 there, and 1920 there. Perfect, done. Bottom chord, this bottom chord. So we move to the top chord, linking for 2 and 4. 2 involve U3, U4. The 4 involve U8, U7, U8. So U3, U4, U7, U8, F3, F4, F7, F8. Yeah, that is. U3, U4 is here. U7, U8 is there. Right. So yeah, you just need to relax. This is actually a good problem that you start when your brain is blank, because you just go ahead on and on and on, fill things in. done with the first one. Then you move to this one, 7, 8, and what? 11, 12, right? 7, 8, 11, 12. 7, 8, 11, 12. Okay, so this is equals to 2 times this one. Okay, 11, 12 is here. I don't change this index indices. I think you know what I'm doing. Oops. Okay, and this one, which is this one here. But basically I know that this one here is going to be the same as that one there. No. Because when I put the third element on top, okay, that's gonna double those 4 entries. 11, 12, 15, 16. 11, 12, 15, 16. So this is here. This is there. And you have another member, I know. So that's gonna be making this one double. Okay. So what? 15, 16, and 17, 18, right? 17, 18 is there. Yeah, just on and on and on and on and on. That's it. Done for top and bottom chord here. Right. We move forward to the top and bottom chord on the right hand side. So we have nothing better to do than just copy the whole thing and come back down here. The point is that the direction cosine is going to change, and what is going to be starting node. I did the plugging in, seems to be just nice and easy, but I am consistent with the node numbering. Okay, so the starting node has to be consistent. If you just switch things around, that could be the catastrophe. Now here for this one, so let's do the starting node on the left and then ending node on the right, so the more number will be on the right ending as the ending node. So here for the cosine is positive, but the sine value is negative. So okay, yeah, it changed automatically already. So like this. Which one we start first? Maybe this one first, top chord, and then we follow by the bottom chord. For top chord, now we have what? 17, right? 17, 18, and 21, 22. 17, 18, 17, 18, which is here. So start here. I'll clean this up. (17, 18, and 21, 22. 21, 22. And not only that, we are going to start our class at 7:30. We are going to have class on Tuesday in the morning before Professor Penning's class. Well, this room is free. We shouldn't leave the room free. Okay? in the investor point of view, right? We shouldn't leave the space unoccupied. So let's make use of this room. So we have class on Monday, Tuesday, and Thursday. And if we can find other spots we're going to have more. All right. Next element. Well, that fit your purpose, right? When you write statement of purpose, you want to have class, you want to have like a master study, and this is it. I am satisfying your purpose. Next one, 21, 22 and 25, 26, 21, 22, 25, 26, 1, 2, 5, 6. Maybe I freeze pane over here. View. Where is the freeze pane? Okay, freeze pane over there. Okay, great. 21, 22, 25, 26. Okay, so this is equal to 2 times this, which is identical. Okay, 25, 26 here. And this is going to be pretty much like this one, because we find that later on 25, 26 is connecting to this one, okay, via this element. So that degree of freedoms, that entries, those entries are double. All right, this is what 29, 30. 29, 30. Basically, I just do this thing. Copy this and paste this. Yeah, you can change the part of array. Okay, fine. I can just okay. Just do it this way. Need to be, and we are talking about this, right? We're gonna have another one there, so this one is going to be identical to this, and the last one, okay, be patient with it. The last one, 33, 34. Okay, so 29, 30 and 33, 34. 29, 30 is there. 33, 34 is going to come in. Yes. Done with top chord. Work on the bottom chord next. So 10 to 12, which is 19, 20 and 23, 24. 19, 20 is here, right? 19, 20 is going to come in, and 23, 24 is going to be here. This is equals to 2 times. I know that it's gonna happen. This thing is going to double. Right? What else? 27, 28. Okay. 27, 28, which is this and this. Just drop in. Just drop in. There's nothing more. This is just the process that computer should do, but we just do it by hand. Move over to 27, 28 and 25. No, what? 31 and 32. So 31 and 32 is here. Okay. Oh, but I guess this week the GTE people are not around because they went out for the field trip. actually we should use this opportunity, but I don't know. There it is. Last one, 31, 32, and what, 35, 36, right? 31, 32, 35, 36, so 35, 36 here, right? And there it is, done. Yes, okay. Done with these top and bottom chords. Now we move over to maybe the incline member. The incline member here, I think we can find out the geometry. This point here, the height compared to point number 1 is what? In total 5, so this is 1.25, right? You break down into 4 identical lengths, so this is 1.25 in height. And how about this horizontal distance? Horizontal distance is 12 over 4, so it's 3, right? So horizontal is 3, but you don't want this, okay? 1.25, you have 5 minus 1.25, so you end up with 3.75, which is the relative location between this point and this point. So it comes down by 3.75, and horizontal distance is 3, right? It doesn't look like that in geometry, but 1.25 in here, right? 1.25 twice, you get 2.5, you get 5, so that's perfect. And actually this is made to the scale, but it just doesn't look like 45 degrees. Almost, it is just almost 45. Okay, fine. Right, copy this thing down. I need to unfreeze the pen. Yeah, okay. So this is top and bottom chord on the right side. Diagonal member on the left side. For diagonal members, we know that they have just the EA, and the length is this is equals to EA is equal to 1. The length is, okay, let's figure out the length first. So vertical distance is 3.75, horizontal distance is 4, right? Or 3. It's 12, right? 12 divided by 4 is 3. Okay. It doesn't look. Huh? Oh, this is 2.5, right? Oh, 2.5. Okay, so okay. Now different. So 2.5 minus 1.25, then you get 1.25. All right. Okay, and then here is 3. All right, that makes sense. So the length is equals to, this is which one? Okay, right. So right, the length is equal to square root of 1.25 square plus 3, right, square, which is 9. 3.25 exact. Okay. So that is equal to 1 divided by 3.25, and this is equals to minus of this one equals to this one, and this is equals to this one. Okay, how about the geometry? I'm gonna use this as a starting node. This is an ending node, so it's gonna have the minus. For the sine value is minus. Okay, and for the cosine cosine value 3, right, is equals to 3 divided by the 3.25. 3.25 is a diagonal member length. There it is, same. Actually, it turns out to be exactly the same. Equals to minus what? 1.25, right? Divide by this value, yeah, 385, the same. This is it, and this is it. Okay, right. What is this? So it is taken care of the thing in here already. Okay, then we can go ahead. Diagonal members 2, 3. 2 means U3, U4, and U5, U6. Okay, U3, U4, U5, U6. Great, easy to, yes.
The matrix still multiplied by 4 over 13.
Which one? Which one? This one multiplied by
4 over 13.
Oh, great, great, great. Eagle eye. Great, thank you. Okay, yeah. Thank you, Dustin. So, 3, 4, 5, 6, right? Equals to this. Done. What next? Well, we are lucky the number 3 is not connecting to number 4. Okay, this element 2 and 3 connects 4 and 5. 4 is what? 4 is 7, 8, 9, 10. Okay, 7, 8, 9, 10. 7, 8, 9, 10 is here. Right? No. 7, 8, 9, 10 like this. So no interlapping. No interlapping is good. So it is quite easy for us to drop in, so there is nothing. Next one, 11, 12, 13, 14. Right. And the next one, 15, right? No. 15, 16, and 19, 20. 15, 16, and 19, 20. There it is. Okay, done with diagonal member on the left. Well, we move to diagonal member on the right. Copy this and come down to here. Right, so just do things systematically. Workflow is going to be not brutal. On the right, starting here, ending there, that is going to make positive values for both sine and cosine. I think nothing left. Okay, nothing's wrong left here. All right. Then 19, 20, 21, 22. 19, 20. I'll freeze paint here. View freeze paint. 19. No. Unfreeze paint first. Okay. 1920 is here, and then 21, 22, right? This is equal to this. Next. So 23, 24, 25, 26. 23, 24, 25, 26 is here. Next one. 27, 8, 29, 30. And the last one, 31, 32, 33, 34. Done for the diagonal member on the right. Now the last one is the vertical member. Yeah, I switch this. Okay, 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Okay, fine. Next one. Oh, unfreeze, but there's nothing left. Here it is. I just zero out everything. Haha. Vertical members. Actually, truss element is quite easy to deal with. This is 2.5. 2.5 will be there. EAOL is just 1 EAOL. Now the angle, okay, let's take a look. Now it is going to be sensitive, I think, if you switch around this. So let's see. 1, 2, starting node is 1. Then the angle is 90 degree. 90 degree. The cosine of 90 degree is 0 and the sine is 1, right? In contrast, this member, if we just use a starting node here, well, I think it is. It might not be that sensitive. Okay, so we just need to see if it is symmetric about this axis, then we don't really have to care. Start first with 1, 2. Wow, great. 1, 2, and 3, 4, 5, 6. So it doesn't touch. Okay, 1, 2, 3, 4. That is 1, 2, 3, 4. And then the second one, 5, 6, 7, 8. And the third one, 9, 10, 11, 12. So you just go like this. 9, 10, 11, 12. And then 13, 14, 15, 16. And then what? Now you have the 9, 10. Okay, the node numbering is just going backward in the other direction. -1. You put the -1, it doesn't alter your stiffness matrix after the transformation. Okay, but you just need to make sure that everything is right. Okay, finally it turns out that it is the same, so you don't really have to be, well, you have to be serious, but it just doesn't change anything. So 17, 18, 19, 20. You just want a copy? This one is okay. What next? 17, 18, 19, 20, 21, 22, 23, 24. Okay. It's the same, so I just a little sloppy. freeze pane here. Okay, what next? Which one? 21, 22, 23, 24 already. 5, 6, 7, 8, 29, 30, 31, 32, 33, 34, 35, 36. Okay, so everything is gonna be just repeating just like this. I will not switch back and forth. And there you go, the last one. Okay, we finished the stiffness matrix plugging in process. We are going to move forward to the system stiffness matrix. So we have this one add up with this one, add up with this one, add up with this one, and add up with this one. Just that. We don't have spring. Can I fill without formatting? And there it is, without formatting. Okay, so your stiffness matrix just look like this for your whole system. You smile, you enjoy it, right? So how many boundary conditions do we have? 1, 2, 3, 4, 5, 6. That's it. Add row and column to accommodate boundary conditions. 1, 2, 3, 4, 5, 6. Okay, here I'll put that and zero it out. That's it. And 6, right? 1, 2, 3, 1, 2, 3, 4, 5, 6. I am slow in Excel, and if I okay, that's it. Zero it out. Boundary conditions at 1, 2, 3. Horizontal. 1, 2, 3. 1, 2, 3. One, 2, 3. Here, 33, 35, 36. 33, 35, 36. Let me freeze the pane again. It's just too many. Freeze pane here. 33. Okay. 33. Well, we're supposed to be here, right? 33, 35, 36. And that's it. 33. 33 is this one here. 35, 36. Anything? In the top, I didn't put minus. Which one? Oh, okay. Okay. So it. Okay, thank you. This is 0, right? Originally it's a 0. Oh, okay. The row shift. Okay. Third 1, 2, and 3. Okay. Thank you. Okay. Okay. Thank you. Yeah, just should paint nice and clear. Okay. View unfreeze pane. Force vector, right? The next part. So force vector, where? Well, I put it here. 0 it up first. For now. No prescribed displacement, so they are all 0 here. Now come back. See pi over 6. 0.02 EA, right? 0.02, we break into 2 components. So 0.02 multiplied by first horizontal component, which is 1 over 2, right? For pi over 6, 0.5. And this vertical component is 0.02 multiplied by previously it is cosine. Yeah, previously it's cosine. Okay, it just switch around. Cosine of pi over 6, but it has to be the negative. Okay. This side is negative. Minus. Okay. There it is. So 7/8. This is horizontal and vertical. 7/8. Okay, you have 7/8. What else? 11/12. 11/12. What else? 15/16. What else? 18. 17/18. Just here. What? 17/18 what? Oh, 0.1. Yeah. But okay. Yeah. Now force from the left side, maybe the wind that attacks this roof is incorporate. Now 0.01 straight in vertical direction, so this is 22. 22 equals to minus 0.01. What else? 26 and 30. 26 put in here and 30 put in there. So forces are plugged in already right now. We will find the solution MULT of M inverse of the inverse matrix is for this one. Okay, close the bracket and you multiply it by the force. I cannot click this cell. Okay, fine. Let's just edit it. So not 202. This is what, 202, right? So I make it 201. Okay. That's it. U1, U2 support, right? U3 support as well. It comes to close to 0 numerical issues. These two and this one support, right? Okay. You get all support reactions. Okay. What did I ask? All displacements and support reactions should be replotted. So reactions are here. Okay, done. Next, problem number 4. You can do this one, right? Of course. So you add up 35 more points, then that makes 70 plus 40, 110 plus 10, 20, 130. So if you make more than 100, then you get just 100. And that's it for the, well, how much time you want for the last one? Maybe 20 more minutes, right? So everything can be fit in 2 hours. Okay, yeah. But I don't, okay, first of all, I don't grade you like this. Let's see, okay, come to here and then I check, and if your displacement solution doesn't match with mine and zero out, I don't do it that way. So I check you on the way. I have like my grading criteria. So I break your solution down into step. But if you intend to submit just the last step, then that is very unfortunate for you that you don't show the procedures on the way. But if you show things along the way, okay, you successfully come up with stiffness matrix of this piece, thing will count. Right? So even though you cannot achieve the final goal, but on the way you can walk to somewhere, then I'll grade you to somewhere over there, right? There's nothing like, oh, not matching with my solution, 0. And then, that doesn't, that is too brutal, and it's just too lazy for the instructor to just grade it that way. Okay, what's your question?
For problem 2, I think the boundary condition is also multiplied by 10.
The boundary condition?
Yeah, because if you multiply the matrix to 10, the negative 1 will also multiply by 10.
Where? Problem 2, negative 1 is here.
When you get the displacement for the matrix M1, you multiply it by 10.
Displacement for the matrix. Okay. No. Because when do the calculations here, the 10 is already in there. That means what you have outside is EA over L, not the 10 EA over L, right?
Yeah.
It is absorbed in these operations already. So we will not have to multiply by 10 again.
Wait, actually when you multiply by 10, the negative 1 becomes also, the boundary condition for the Lagrange multiplier also become negative 10, right?
Well. We are talking the stiffness matrix part.
Yes.
Actually, I can just make it like use the 10 and push the 10 inside and multiply everything in here by 10. It doesn't change anything on the right hand side. It is two different issues, right? For example, yeah, if I just take 0, okay, it is 1, okay, the scaling here is 1, and then everything in here I multiply by 10, okay, then how would that affect minus 1 there?
So the negative 1, the added columns and the added rows will become negative 10,
No. Okay, I did that way and it looked confusing for you, but make it like this. Okay, it is originally the issue about the things inside the.
Because what I did is 10 negative 10.
Yeah. So the things, the stiffness part, okay, is scaled by 10, but on this side it is the reaction R1 and R9. So once you move R1 in there, okay. I get your point. This is get the consequence of that having that 10 out there. Okay, yeah. Then okay, we look at this matter a little bit. Hey, well, yeah, sloppy. Sloppy work leads to the headache later. Should it? Now it is. Okay, just just find the fastest way to fix this. Okay, and then I get the 10. It shouldn't do. Yeah, that is a good tricky way, but you still keep the 10 outside there. You enjoy, you okay with that? If you want to keep it that way, go ahead with 0.1 like this, right? Okay, anything change over here? Okay, now it comes like this. Then I need to take this out. Do I know? Because 10 is out there. Okay, so it should appear over here. Very risky action. Hide things around and then at one point it messed the thing up. Okay, right. Wrong by magnitude of 10. Okay, so this is 3 without formatting. Okay, all right. So 9:28. We can proceed to the nonlinear geometry in this class, right? Okay, so I hook up the iPad and then we have an hour because Professor Pinning class is at 10:30, right? So we have pretty much about an hour. Okay, so nothing more about this. All right, then I switch to the iPad. Thank you for your input, Justin.